NENOMATICA, where mathematics meets YouTube excellence. Here is the algorithm. Case 1. If r is greater than 1, then the logarithm is increasing. So comparing the logs is the same as comparing the inputs. We must also guarantee that the argument on the right is positive. Case 2. If 0 is less than a and is less than 1, then the logarithm is decreasing, so the inequality reverses, and we require that the argument on the left be positive. Why do these cases happen? Because the shape of the log changes with the base. On the left, log base 2 is increasing, so larger inputs give larger outputs. On the right, log base 1/3 is decreasing, so larger inputs give smaller outputs. That is why the inequality reverses. Example: solve log base 2 of open parenthesis 3x minus 1 close parenthesis greater than log base 2 of open parenthesis x plus 5 close parenthesis. We are in case 1 because a equals 2, which is greater than 1. That means, first, make the right argument positive, then compare inputs without flipping the sign. Finally, intersect the results on a number line. Second example: solve log base 1/3 of open parenthesis 2x plus 1 close parenthesis greater than log base 1/3 of open parenthesis x plus 5 close parenthesis. This is case 2 because the base is between 0 and 1. First, make the left argument positive. Next, reverse the inequality when comparing the inputs. Finally, intersect the results on a number line. Important reminder: when we remove the logarithms and turn the problem into a system of inequalities, we must include the domain conditions. If a is greater than 1, we require the right argument to be positive. If the base is between 0 and 1, we require the left argument to be positive. In both cases, the comparison step already guarantees the other argument is positive. Finally, we intersect all conditions to obtain the solution set. Example: first, here is the problem. Step 1. Determine the domain. We need the arguments of both logarithms to be positive. From 1 minus x over 4 bigger than 0, we get x less than 4, and from log base 9 of x, we get x bigger than 0. Together the domain is 0 less than x less than 4. Step 2. Rewrite the inequality by moving everything to the left so we can use a difference of squares. Step 3. Convert the square root into a 1/2 exponent. Step 4. Apply the logarithm power rule. The 1/2 comes in front. Step 5. Unify the bases using the change of base for powers. 1/2 times log base 3 equals log base 3 squared, which is base 9. So the bracket becomes log base 9 of 1 minus x over 4. Step 6. Factor the difference of squares and write 1 minus x over 4 as 4 minus x over 4. Step 7. Combine the logarithms. The first factor becomes log base 9 of 4x over 4 minus x. The second factor becomes log base 9 of 4x minus x squared over 4. Because the base is bigger than 1, the product is non-negative when both logs are non-negative or when both are non-positive. Case A, both are greater than or equal to 0. That means each argument is at least 1. The second inequality simplifies to a perfect square, so it forces x equals 2. Case B, both are less than or equal to 0. With base 9 bigger than 1, that means each argument is between 0 and 1. The second condition is automatically satisfied on 0 to 4, while the first gives x less than or equal to 4/5. Finally, combine both cases under the domain. The solution set is from 0 to 4/5 inclusive, or x equals 2. In this video, we will solve a system that mixes a logarithmic equation and a logarithmic inequality, and we will do it step by step with clear visuals. Here is the system. 4 times the square of log base 2 of x plus 1 equals 2 times log base 2 of y. And log base 2 of x squared is greater than or equal to log base 2 of y. First, the domain. Because we have logarithms, we must have x greater than 0 and y greater than 0. We will also use the power rule of logarithms. Log base b of a to the k equals k times log base b of a. This tells us that log base 2 of x squared equals 2 times log base 2 of x. Now isolate the unknown log base 2 of y in the first equation. From 4 times the square of log base 2 of x plus 1 equals 2 times log base 2 of y. Divide both sides by 2. That gives log base 2 of y equals 2 times the square of log base 2 of x plus 1/2. Next, we convert the inequality into a statement about a single variable. Since log base 2 of x squared is 2 times log base 2 of x, the inequality becomes 2 times log base 2 of x is greater than or equal to log base 2 of y. Substitute our expression for log base 2 of y. We get 2 times log base 2 of x is greater than or equal to 2 times the square of log base 2 of x plus 1/2. Move all terms to one side and clear the fraction to see the quadratic shape. Multiply by 2 and rearrange. 4 times the square of log base 2 of x minus 4 times log base 2 of x plus 1 is less than or equal to 0. This is a perfect square, the quantity 2 times log base 2 of x minus 1, all squared, is less than or equal to 0. To build intuition, let t be log base 2 of x and graph the quadratic. The horizontal axis is t. We plot y equals 4t squared minus 4t plus 1. The parabola opens upward and touches the horizontal axis only at t equals 1/2. Because a square is never negative, the inequality less than or equal to 0 can only hold at that single point. Therefore, we must have 2 times log base 2 of x minus 1 equals 0. That means log base 2 of x equals 1/2. Converting to exponential form gives x equals 2 to the 1/2, which is the square root of 2. Now, compute y using the expression we isolated earlier. Log base 2 of y equals 2 times 1/2 squared plus 1/2, which simplifies to 1. Hence, y equals 2 to the first power, which is 2. A quick check confirms the pair satisfies both statements. In the equation, 4 times 1/2 squared plus 1 equals 2 times 1. In the inequality, log base 2 of x squared equals 1, which is indeed greater than or equal to log base 2 of y, which is also 1. Therefore, the unique solution to the system is the ordered pair open parenthesis square root of 2, 2 close parenthesis. Recap: domain first x and y are positive. Isolate log base 2 of y from the equation. Use the power rule to rewrite the inequality. Substitute to get a quadratic in t equals log base 2 of x. Recognize the perfect square. A square is non-negative, so less than or equal to 0 forces equality, giving t equals 1/2. Convert back to x, and then to y. Done. Example: we will solve this inequality for the parameter a so that it holds for every real x. 1 plus log base 5 of x squared plus 1 is greater than or equal to log base 5 of ax squared plus 4x plus a. Step 1. Replace the 1 with log base 5 of 5. Then use the product rule for logarithms. That gives log base 5 of 5 times x squared plus 1 on the left. Since the base 5 is bigger than 1, the logarithm is increasing, so we can drop the logs and require two things. 5 times x squared plus 1 is greater than or equal to ax squared plus 4x plus a. And also the argument on the right is strictly positive. Now, rearrange the first inequality. Move everything to the left. For later convenience, multiply by -1, which flips the inequality sign. So it becomes a minus 5 times x squared plus 4x plus a minus 5 is less than or equal to 0. Let us quickly test boundary values. If it equals 5, the first inequality becomes -4x is less than or equal to 0. So x must be non-positive, which fails for x equals 1. So it equals 5 does not work. If it equals 0, the second inequality becomes 4x greater than 0. So x must be positive, which fails for x equals -1. So it equals 0 does not work. From here, we follow the standard approach shown in the model solution. We consider 0 less than a less than 5. For the first inequality to hold for every x, since a -5 is negative, the quadratic must never cross the axis, so its discriminant must be less than or equal to 0. The discriminant is 16 minus 4 times a minus 5 squared, so 16 minus 4 times a minus 5 squared, less than or equal to 0. This simplifies to a less than or equal to 3 or a greater than or equal to 7. Intersecting with 0 less than a less than 5 gives 0 less than a less than or equal to 3. Next, we require the second quadratic to be strictly positive for every x. That happens when it is positive and its discriminant is negative. Its discriminant is 16 minus 4 squared less than 0, which yields absolute value of a greater than 2. because we already restrict to positive a, we get 2 less than a less than 5. Finally, we intersect the two conditions. On a number line for a, mark the important points -2, 0, 2, 3, 5, and 7. The first condition gives 0 less than a less than or equal to 3. The second gives 2 less than a less than 5. Their intersection is 2 less than a less than or equal to 3. Therefore, the inequality holds for every x if and only if it is between 2 and 3, including 3. In this lesson, we will solve a logarithmic inequality exactly following the steps shown in the source solution. Here is the example and the multiple choice options. Step 1. Move 1/2 log x to the left side. Step 2. Combine the like logarithmic terms. Step 3. Use the power rule of logarithms to bring the 1/2 inside as an exponent. Step 4. Because the base of the logarithm is greater than 1, we can drop the logs and compare the arguments directly. Step 5. Square both sides to solve for x. Now, we select the correct option. Option 3, x greater than or equal to 4, is correct. In this example, we will solve a logarithmic inequality by following the exact 3-step chain shown in the prompt. The question says, for x greater than 0, which statement is always true? We will keep the options on screen, then reproduce the 3-line solution. 1. Derive 1 plus x is less than 10 to the x. 2. Take the logarithm to get log of 1 plus x less than log of 10 to the x. 3. Simplify to get log of 1 plus x is less than x. Finally, we will mark option 3 as correct. Step 1. For all positive x, we use the well-known inequality. X greater than 0 implies 1 plus x is less than 10 to the power x. Step 2. Apply the base 10 logarithm to both sides. Because the logarithm is increasing, the inequality direction stays the same. Therefore, log of 1 plus x is less than log of 10 to the x. Step 3. Simplify the right side since log base 10 of 10 to the x equals x. We obtain log of 1 plus x is less than x. To build intuition, let's look at the graphs for x bigger than 0. We will plot y equals x in green and y equals log of 1 plus x in blue. Notice that for positive x, the blue curve stays below the green line, matching the inequality. Therefore, the statement that always holds is log of 1 plus x is less than x for x greater than 0. That corresponds to option 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.